Welcome to the Agentic AI video series. Today's topic is BNA, Business News and Analysis AI Studio. Subtitled, From Tool to System. It works, it's trustworthy, it remembers, it decides. Based on the academic courseware by Professor Shihmin. In this module, we examine a paradigm shift in product management education. As AI coding agents reduce implementation costs close to zero, the core value of product engineering shifts from technical building to defining what correct execution means. We explore how PMs specify JSON schemas, build 4 defenses of verification, calibrate confidence thresholds, and govern autonomous agent loops. Let us step through the 4-day curriculum architecture. Module 0 establishes the executive summary of the BNA SaaS workshop. When coding agents make implementation fast and inexpensive, product management judgment becomes the primary scarce asset. Coding agents can write verification loops in minutes, but they cannot determine whether confidence thresholds should be 80 or 60. They cannot select the 5 items in an action space, nor set hard budget caps or decide when to wake up a human. To address this shift, the workshop restructures its 24-hour budget. Judgment-oriented hours are expanded from 27% to 59%. Implementation hours are compressed without increasing total time. To prevent technical debugging from consuming decision training, instructors enforce a strict 15-minute rule. Pre-built code snapshots align participants at module checkpoints. This guarantees that time is spent on product specifications rather than syntax. PMs learn to define verifiable success criteria for AI systems. Module 1 clarifies course positioning and the PM mindset. Target participants are business students and early career product managers, not software developers or forward-deployed engineers. This positioning dictates the entire curriculum emphasis. In traditional software training, building a dual-language web application required hours of manual syntax and environment configuration. Today, vibe coding allows agents to generate core functions quickly. However, vibe coding lowers syntax barriers without lowering specification rigor. Engineers and AI models cannot guess unwritten standards. If a product manager does not write down the criteria, no standard exists for the system. Participants learn to translate subjective feelings like, "This output seems generic," into explicit, checkable conditions like, "Every insight must cite a verbatim quote." This translation skill forms the backbone of product management rigor. It establishes clear boundary conditions for AI outputs. Module 2 covers the first milestone. It works. Business frameworks like BMC and PESTEL must be transformed from mental concepts into executable AI skill specifications. A vague prompt like, "Analyze this news," yields unpredictable outputs. A structured skill specifies exact JSON schemas, field ordering, field constraints, and explicit rejection criteria. Security is strictly enforced through API key isolation. Keys are entered in front-end settings, saved in local storage, and never hard-coded into source control repositories. Participants formulate an acceptance checklist across 3 layers. The format layer checks JSON schema validity and dual-language fields. The fact layer verifies verbatim source quotes against original text. The logic layer checks reasoning consistency between facts and conclusions. This checklist evolves directly into automated verification specs. It ensures that the core application functions reliably. Module 3 establishes the second milestone. It's trustworthy. AI models never express uncertainty. Their tone is always confident. Therefore, trust must be calculated by system verification. 4 automated defenses are integrated into the architecture. Defense 1 mandates a source quote field containing verbatim original text. If the quote cannot be string matched in the input news, the insight fails. Defense 2 performs hallucination detection via a secondary API call. Claims are categorized as grounded, unsupported, or conflicting. Crucially, this secondary call must use an independent conversation context. Reusing the original context causes self-defense bias, inflating scores. Defense 3 computes a quantitative 0 to 100 confidence score. Interface badges display green for 80+, yellow for 50 to 79, and red for under 50, with unsupported claims rendered with dashed underlines. Defense 4 performs cross-reference verification across dual news sources. Contradictions between reliable sources are flagged as market signals for human review. Module 4 details confidence threshold setting as a quantitative PM decision. Thresholds are product decisions, not arbitrary technical parameters. They must account for asymmetric error costs in business. Publishing false news destroys user trust instantly, while blocking valid news reduces product utility. Because these costs are unequal, thresholds cannot simply default to 50%. PMs calibrate thresholds using empirical sample data. Participants annotate 10 to 15 historical analysis outputs, marking whether they would confidently publish each item. Cross-referencing human decisions with system scores reveals empirical thresholds. The architecture enforces a 3-tier threshold structure. Scores 80 and above trigger automatic morning brief publication. Scores between 50 and 79 route to agent loops for auto-query retrieval. Scores below 50 route directly to human operators to conserve compute budget. This quantitative calibration produces defendable, explainable product metrics. Module 5 covers the third milestone. It remembers. Foresight analysis requires structured historical data across multiple periods. The knowledge base adopts a 3-tier architecture: macro trends, industry ecosystems, and company dynamics. Every analysis output is automatically tagged across BMC 9 building blocks. This tagging enables structured retrieval by business component over time. Participants learn data modeling discipline before building databases. Planning schema fields early prevents expensive structural revisions later. The storage layer transitions seamlessly from local storage MVPs to production relational databases like Supabase. Database tables store headlines, tags, dual language analysis, and timestamps, alongside verification fields including confidence scores and source quotes. This structured historical record forms the backbone for trend analysis. It transforms isolated daily news into cumulative strategic intelligence. The system builds a persistent memory foundation for performance forecasting. Module 5 further introduces performance foresight and scenario planning. Foresight does not predict a single deterministic future. Instead, it constructs base, bull, and bear scenarios. Each scenario details trigger conditions and leading market indicators. Every forecast requires 2 mandatory schema fields: assumptions and falsifiers. The assumptions field explicitly lists foundational premises. A higher number of unverified assumptions lowers the overall confidence score. The falsifiers field is the core soul of foresight analysis. It specifies explicit market signals that, if observed, completely invalidate the business forecast. A forecast without falsifiers is fortune-telling, not analysis. Falsifiers provide a scientific boundary against overconfident AI claims. If data is insufficient to establish falsifiers, the system returns insufficient data rather than generating ungrounded predictions. Module 6 completes the 4th milestone. It decides. We distinguish between fixed workflows and autonomous agents. A workflow follows pre-programmed branch paths and reports errors to humans. An agent evaluates execution feedback and dynamically alters its next action. An autonomous agent loop requires 3 essential specification elements. Element 1 is the stopping condition, defining when output is good enough. This directly reuses the day 2 publish confidence threshold of 80. Element 2 is the action space, specifying authorized actions. The action space is a strict whitelist, not a suggestion list. Authorized actions include expanding search keywords and widening time windows. Unlisted actions, like querying unverified sources, trigger immediate human escalation. Element 3 is the hard budget cap. Hard caps enforce max retries, max execution time, and max API cost in code. Budget limits must be checked in code logic, never relying on LLM self-discipline. This 3-element framework ensures safe, cost-controlled autonomous agent execution. To summarize today's module on BNA Business News and Analysis AI Studio. First, product management value shifts from coding syntax to defining correct specifications. Second, trust must be engineered through 4 automated verification defenses. Third, confidence thresholds must be quantitatively calibrated using sample data. Fourth, performance forecasts require explicit assumptions and falsifier conditions. Fifth, autonomous agent loops require stopping rules, action whitelists, and hard budget caps. By mastering these principles, PMs bridge business strategy with AI engineering. This concludes today's module on BNA AI Studio by Professor Shihmin. Thank you for watching, and see you in the next module of our Agentic AI series.